So I'm Dean Wampler. I work for Lightbend, which is the company behind Scala, and I actually do big data for Scala at Lightbend. Because it turns out that Scala kind of suddenly found its maybe best niche in the big data world, almost by accident, because a lot of the big open source projects like Spark and Kafka were written in Scala. And then it turns out, let's say a subset, certainly not the majority, but there's a certain core of people who actually really like Scala for data science. So typically big data environments break up into, let's call them 3 groups. There's always the operations people who keep things running. Can't forget about those guys, gals. Then there's like the engineers who design the plumbing, who know how to make Kafka work, who know how to debug stack traces in Spark, which is actually a core competency, things like that. And then there are the data scientists, who are the ones who do like the machine learning models, the statistics, and all that. And it's more common, even in Spark, to work in Python and R, languages like that for data science. That's what they're used to. But developers are going to stick with typical JVM languages like that are more JVM-centric, like Java and Scala. And we've seen at Lightbend that the Spark in particular, because it's so hot right now, has been driving adoption of Scala. But this is really a talk about why, well, it's kind of a mixed talk in a way. It's why is Scala really nice for big data, but also in general, what are some of the advantages it has over other languages? So there's a little bit of something for everyone. There's really only 3 slides, and then I'm going to do just demos the whole time. The first one is the usual reminder to rate the session, post questions to the speaker thing. I'll quickly grab it when we're done, or we can just do it the old-fashioned way. And any feedback, put it in there as well. Let me see it. And when you get the slides, the thing I'm going to demonstrate will all be at this Git repo, Scala for Data Science, in my GitHub account. And that's it for the slides. Maybe I'll put that back up at the end. But what we're going to do actually is use a notebook metaphor for the demonstration. So this is something that's not too familiar to most developers, but data scientists love these things. It's really an electronic version of what scientists have been doing forever, which is keeping lab notes in notebooks. You guys probably did this in like chemistry and physics classes. The nice thing about them is you can do stuff like interleave commentary. Like if I go to the top of this is all markdown. I can edit it in the usual markdown way. Then I can embed code and run that. Intermix that, and even do graphs, plot data and so forth. So, as you can imagine, if you're a data scientist, especially like the plotting part can be really great. But any language that supports a REPL, an interpreter, it's really nice to, I think, to work in this way. If you've ever spent a lot of time working in an interpreter for any of the languages except Java, like Python, Scala, Clojure, Ruby, after a while it gets really tedious. It's great for messing around a little bit, but what if I want to edit something and rerun it? It gets to be difficult. Notebooks actually take you a lot farther. I can easily go back and edit a line, rerun that cell, as they're called in this particular notebook, reevaluate everything if I want to, and so forth. So that's why I decided to do this particular demo, because it's partly aimed at maybe people who aren't used to using these to sort of evangelize the idea, but also to show how useful they are. So I've actually got a couple here. This particular notebook happens to be for a Spark exercise that I wrote for some training Lightbend did. Shameless plug if you want to buy training from us, we can sell you that too. But actually the reason I brought this up is really to show you sort of what a real notebook actually looks like. I'm using a particular notebook environment called Spark Notebook that's sort of Scala-centric. You may have heard of Zeppelin, which is much more popular actually in big data. And if you ever even talk to a Python person, you've probably heard of Jupyter, or what do they call it now? Oh, it's not Python, now they call it Jupyter. So, but it's the same idea. Edit cells, evaluate them, mix documentation, SQL queries, anything like that together to get the whole experience. This particular notebook basically riffs on sort of the hello world of big data, which is word count. I've got a whole bunch of documents, I'm going to suck them in, tokenize them to words, and then count all occurrences of the words in the thing. So it would be like the very first thing you would write if you were building Google killer, some sort of search index like that. Actually, no, you wouldn't use word count. You use the next thing, which is called inverted index, because the problem with word count is you forget where you found stuff. All you care about is counts. The reason I brought this up, though, is that I had people in this exercise go through and tweak this algorithm a little bit to do additional things. In this particular case, they would count words, get the counts, and then they would group over the counts. And what that means is, how many words appear twice? How many appear 3 times? How many appear 10,000 times? That kind of stuff. And what's interesting about this exercise for data scientists is that it kind of gets to the natural behavior of language. Like some kinds of words appear all the time, appear a lot. Other words are much more rare, but maybe more interesting because they're more unique kind of words. And so here's just what a typical Scala program, Scala Spark, looks like. There's some setup I did up front here, but I'm basically loading some data that I have with this exercise. Tokenizing it by words is what this is doing. Creating tuples, word, in this case, taking each word and making a tuple out of it, where the word is the key and then there's a seed count of 1. Reduced by key is an optimized group by that just grits all the words together because they're in the key position and sums up all those counts. So now I have my words and my counts. And then the rest of the logic for the next few lines is, all right, I don't actually want to sort by words anymore. Now I want to sort by counts, or in this case, group by counts. So this is this group by statement. Actually, I can make this a little bigger. Might be a little hard to see in the back. Yeah, hopefully that's a little better. Group by key in this case, because I've already said use the count as the key in the previous line. Now I'm going to get all the groups of words together that appear twice or whatever. Sort them, by this count. In this case, I'm sorting descending. That's what the false means. And then there's some final output that I do. And caching is an optimization. What's interesting, though, about this data is that then you get down and I write it out to files, which is not that interesting. If you'll let me get this to scroll a little better, there we go. And if you actually plot this, what you find is that way down here, it looks something like this, where you have some words that just appear an enormous number of times, and then it quickly falls off, so you get something that looks useless. How am I going to interpret this? But notice I'm graphing this data as I'm looking at it, and I'm thinking, how can I get something more meaningful out of this? Well, the first thing that a typical data scientist too would do is say, maybe if I plot logs, then this sort of extremity would disappear. And this first one, we're plotting, I think it's just logs on one axis, but the interesting one, notice I can even embed LaTeX. This is the usual LaTeX stuff for those of you that, like me, wrote a dissertation in LaTeX. Anyway, so I can embed formulas. Let me evaluate that cell again so you can see the formatting just disappeared. There it is. So it looks like, regular math. But if I actually plot log, it gives me a straight line, more or less, except for a lot of noise. That actually turns out to be a power law distribution, which is the idea that some things really occur a lot, and then other things tailor off really fast. And they tend to form a line. And if you remember this was high school math, you can calculate the slope of the line because you took a log, you can get the exponential factor. Is it really like going up as a factor in the square or whatever? And then if you actually looked at this data in detail, you'd notice that these things that appear a lot are words like the, he, and all the so-called stop words that nobody cares about because they don't tell you anything. This is actually the plays of Shakespeare. And if you go down here and look at these words, which the words are actually lost at this point, you'd see that it's like Hamlet and Ophelia and Henry and those kind of more specific words. Anyway, I just wanted to show you this to point out why these notebooks are attractive as a tool. But then it raises the question, well, what's the best language? Here I use Scala, but most people would use Python or maybe the R language. So instead, I wrote another notebook that actually walks through some of these advantages of Scala over other languages. The four that Spark supports are Scala, which it's written in, Java, Python, and R. And Java 8 is not so bad because it has lambdas now. If you didn't have lambdas, that block of code where I was like grouping things and reducing, that would have been like several hundred lines in pre-Java 8. In Java 8, it would be maybe 3 times as much. But there's a bunch of things that just make it so fast to write these kind of data applications with really relatively little amounts of code. And Scala has a unique set of capabilities that enable that, but then some of the other languages do too, to a degree. So this is really sort of an essay, if you will, in the strengths and weaknesses of Scala. And I'll very specifically finish with weaknesses too, because it's not perfect. Well, the first point is that Scala is kind of a nice compromise, or let's call it, actually let me make this full screen to get just a little more real estate here. Full screen. There we go, you can see a little better now. People debate this in the functional programming world, but it is kind of a nice, pragmatic balancing of object-oriented and functional programming. It turns out that, in my opinion, big data is really kind of the killer app for functional programming. About 10 years ago when everyone was talking about it, what they were obsessing over was the end of Moore's Law, and suddenly we had to get better at concurrency. And people who were thinking about this problem realized, actually sort of the functional style is better for concurrency because it emphasizes things like functions that don't have side effects, that only modify what you pass in, or not even modify, but work with what you pass in and then return something new, but don't change state. Immutable values, where if I create an object in a state, I'm never going to mutate it and risk having somebody mutate it simultaneously, leading to inconsistencies. Referential transparency is the idea that, if I call a function with a value and it always gives me the same answer for that input, then I can actually substitute a cached answer in subsequent invocations. And it also has implications for, not only can I do caching very nicely, but I can even move that function around because it doesn't have much connection to the rest of the world. I can call it anywhere once I know it's working. Higher order functions are the idea that, if I'm doing a map over a list, I pass a function to map. The function is a value. It's called higher order because it's a function rather than a regular value. And of course, map applies that function to each value in my list. We'll see all examples of all of these if any of them aren't clear. And then the really interesting idea that's, here I am, I do this all the time. I double click things to highlight them and then it goes into editor mode, so I'll keep doing this. But so here's more markdown, in case you don't know markdown. But the different idea from object-oriented programming that it's great to actually separate operations from structure. So I can have like lists or trees or maps, and I can have iterators and map routines and flat mappers and reducers and stuff, and just uniformly apply them, which turns out to be fantastic for composing the kind of stuff that we build with data. But it turns out that pure functional programming tend to be weak on facilities for modularization. How do I actually build up big applications and have nice boundaries so that it's not just everything global? And the decision Scala and some other languages have made is to continue to use objects as a modularity mechanism. In the case of Java versus, say, F# or OCaml, Martin Gursky, who created Scala, said, all right, we'll just basically let you do everything you can do in Java. We won't try to say only use objects in a certain way. We'll give you full facility with objects, but we'd really like to encourage you to use functional programming whenever you can and use objects as your modularity tool. And it generally works pretty well if you kind of follow good practices that way. A few of these cells, here's another cell, actually compares this to some of the other languages. And most of what I just said is more or less true of Python. You can do a nice balance of functional and object-oriented programming there if you want to. Java is starting to catch up with, now that it has lambdas and now that they have streams that give you more of a functional style collection interface, if you will. The R language is written by statisticians, so it doesn't really fit the usual paradigms of object-oriented and functional per se. It's more of a statistics language, kind of a specialized language in the way that Matlab is kind of specialized for matrices and stuff like that. But there are some hooks that you can do sort of a version of object-oriented and standard functional programming if you want. Now, a subtopic of this functional versus object-oriented trade-off is an interesting idea called traits that are sort of the replacement for interfaces in Scala. Now, before Java 8, so another thing Java 8 added is you can now define default methods for the interfaces that you define in your interfaces, or you declare, so let me say it more precisely. Used to use this terminology a lot in C and C++, where you had a declaration in a header file and then a definition, in the C code. Same is true here. In Java, it used to be that interfaces could not actually define a function, they could only declare it. And that became a problem because if I wanted to have a common abstraction for logging, let's say, a lot of times it's just obvious what I want to mix in as the implementation, but there was no mechanism in the language to do this. I always had to do some sort of hack to implement the logging interface, but then delegate to some helper method or helper class or something. But Scala, and now Java 8, lets you actually attach definitions to these declared functions. And that enables a mix-in architecture where I can mix in behaviors like logging or persistence or whatever more seamlessly, implement them separately, and do composition rather than inheritance. There is actually some other things that traits give you beyond interfaces, like you can have fields in traits. So I can carry a long state, like here's the logger I'm going to use. Whereas in Java 8, you still can't have fields in these interfaces, just methods. But there are ways to get around that limitation. This point 1b is something that a friend of mine mentioned who's been doing a lot of Java stream programming. So this is like a new thing they added to the collections API, where you can take a regular Java collection and turn it into essentially a lazy stream where you'll just pull off values as if just a stream of data coming in. And then you can do this sort of functional kind of processing, like map over the stream, flat map it, filter it, and so forth. And he found it to be somewhat awkward to go back and forth between these metaphors. Whereas languages that were designed more with functional programming in mind, like Scala, tend to make that more of a first class, and this is the only way you do it, is you operate with these operators. And here's let's actually look at some examples. So let's talk about functional style collections. So I've got a little method here I stole from Wikipedia to determine if an integer is prime. It's actually not a very good method. It's kind of crude, but it does the job. And if I want to make sure this compiles, in this case I can just do shift return, or I can click this arrow button here, and just to verify that it's working. So it compiled successfully, it tells me how long it took and so forth. But it's just a Scala method. It does some of the things that we said are good for functional programming. There's no side effects. I use encapsulation of a second method inside here, so I don't have that function leaking through the abstraction. There's a bunch of things that are nice about it in a functional way, but for the most part, it's just sort of a standard method that you might write in any of these languages. So remember what I said about having higher order functions. Here I'm passing a function to map that's going to take each of these integers that I'm generating from 1 to 100 inclusive. I'm going to map over those, and for each of those integers I'm going to call this function that returns a tuple. And this is one of the things I'll get to later, but this is really nice in Scala that you have this literal syntax. If I put stuff in parentheses, it automatically creates an instance of a tuple for me. In this case, the integer that I passed in and whether or not it's a prime. So it'll be integer, boolean will be the type. Notice the periods at the end. This is really one big expression. And then I'm going to group over whether or not it's prime. So I'll get two big records, one with all the non-prime numbers and one with the primes. And then the last thing I'll do is map over that tuple, and I can get, no, actually I saw that here. Here's how you get the second element of the tuple, _2, here's the first, and so forth. And they count from 1, that's just sort of a historical thing, as opposed to 0. And the last thing, though, I'm doing with this map statement is I just want to see true, false, and the first thing is going to be the true, false, because that was what I used as a key in the group by. And then how many of them do I have? And ironically enough, look at the number, it comes out that 75 are not prime and 25 are prime. So it's exactly 3 to 1 from 1 to 100, which I thought was kind of an interesting result. It just fell out. What this notebook and some of the others will try to do is when you return, in this case, a map, it will try to show it in a table for you automatically, and that's what it's done here. Not terribly exciting in this case, but pretty useful if I just want to see a representation of the data. Excuse me. Okay, let's look at the same thing in Spark. So here's so Spark was basically inspired by the Scala collections. Notice these 3 lines: map, group by, and then map again, with some setup to actually create my collection. And in Spark, it's basically the same code. There's some setup on the first line, and then the exact same 3 methods, and then the final line I'll explain in a second. Spark context is the entry point into my cluster, or in this case, my local machine. Parallelize is sort of the analog of just computing a range and turning it into Spark's own internal data structure called it's called an RDD, and you can actually see the type here. That stands for Resilient Distributed Data Set. Resilient in the sense that if you lose a node, it can recover, reconstruct what was lost, and distributed because I have the illusion of one big collection of memory, but it's actually partitioned over a cluster. But once I set that up, then I have exactly the same methods at my disposal. So I could have even put this code in a library. The typing is actually a little different. It wouldn't quite work to go from Scala collections to Spark. But because of type inference, I don't care. I just copy and paste, and it actually works. The reason this is here, after I've constructed this RDD, what collect does is it turns my big RDD into a local Scala collection. One major difference between these RDD operations and the Scala collections is the RDD operations are lazy. They don't do anything until I say, give me results. And that's what collect does. Whereas Scala collections are eager, so they would have ran right away. So I did have to do a little cleanup at the end, if you will. But otherwise, once I have these metaphors of, mapping and flat mapping and all that, it just transfers beautifully over to my big data environment. And we get the same results, thank God. It's not a probabilistic result in this case. Okay, so that's kind of cool. That inspiration, looking at the Scala collections, the guys who created Spark said, these work for the kind of problems we're trying to solve, manipulating data in sort of it's not really a stream model yet, but it is the idea of, I'm going to decompose this. I need to get from here to here. I'm going to decompose it into steps, and I can have all of these operations at my disposal to do that decomposition. So they basically copied the Scala API. And Python and R code would look kind of very similar. No real winners there. But Java, until they added lambdas and the stream API, it was not at all elegant to do this in Java. The Spark API did give you these kind of methods in their Java API, but it was just a lot more noise trying to create anonymous inner classes for all of these little simple methods. But now that's always gone away. One of the powerful things, though, that Java still doesn't have, although there's rumors, I guess, that they may add this in Java 9 or Java 10, is an actual interpreter. So that instead of just writing a unit test and running an Eclipse or whatever to see what you've got, you can actually just fire up something like this environment, which is actually running the interpreter, or use the Scala command and then interactively work with your data, experiment with your APIs, and so forth. So I didn't even show an example because all the things you've seen so far, I've actually been using the Scala interpreter to do it behind the scenes. And everything but Java has this capability, so that's not really too new. I mentioned this one already, though, the nice convenient tuple syntax, because it's really nice to think of records as being like tuples of data. And even some sort of database theory, you'll see that kind of description. And Scala makes it really easy to just put stuff in parentheses and bang, you've got a tuple. And it's sort of low ceremony. So that's what I've used a lot here. And It turns out Python is almost as nice, not quite as flexible as Scala. R has some tuple types as well, but the syntax is a little less convenient. And Java doesn't have anything at all. And Java really could easily add tuple types to the library. I'm not entirely sure why they haven't. So Spark added one for the most common tuple, which is a 2-element tuple representing key value pairs. And I wrote this in Scala, but basically this is what you would do in Java, in Spark, to instantiate a tuple. But yeah, this is really noisy, right? I don't want to have to do new, mutable pair, get the types right, pass in arguments. I just want to write stuff like this. I can. One of the most powerful ideas in functional programming, and you saw that if you were in Steve Banofsky's talk about Erlang a minute ago, is pattern matching, which lets us not only figure out what we've got when I pass you something, but we can tear it apart into its constituent parts really easily, rather than using like getters and so forth like that. So here I've rewritten the last Spark example to use the pattern matching facility for tuples. So instead of saying group by and then here's your tuple, grab the second element of the tuple, I can use this case keyword, and also I have to use curly braces, it turns out. I'm going to say, I expect, and in this case I know I'm going to always get a 2-element tuple. I'm going to ignore the first field, so I use underscore to say I don't care about it. But notice I can apply a nice name, which in this case, is it prime or not, and then the value that it was pulled out of that tuple will be assigned to primality. And in this case, I'm just going to return that, and that's how I know whether I'm going to group by trues and falses. And I do it again here, matched by primality and values. Again, these are variable names, arbitrary choices, but I can read this code and know what these fields mean, which is pretty nice. And then I just return what I want as the final result. So it's an elegant way of tearing things apart, but it also lets you do things like use useful names for things that are automatically assigned to the pieces. Let's see, scroll.
Sorry, Dean.
Yeah.
You seem to have lost a prime number there. If you scroll up, you only got 74.
Oh yeah, you know why? I thought I fixed this actually. It's because I went up to but not including.
Okay.
So I'll change that right now.
Hooray!
Yeah, good catch. Thank you for that.
It's proving we're awake still.
Yeah, you always have to have somebody in the audience. That's awake at 6 o'clock or whatever. So there we go. Are you happy now?
I'm very happy, thank you.
All right. And just to show that this is pretty flexible, actually in Erlang, every assignment is actually a pattern match expression. You can do that in Scala too. Here I can try to deeply nested tuple, and then just did an assignment on the left-hand side where I just named variables that happen to match the structure, and it just automatically, I can run that again, it automatically extracted all the pieces in a nice way. Pretty cool. I use this a lot. The only catch is I have to know exactly that I have the right number of elements and the right nesting, otherwise I'll get an exception. But if I know exactly what I've got, this is really handy for like having multi-return values from a function and just pulling it apart as it comes back. This is something I don't think you can do in any of the other languages. I don't think Python can do nested tuples, if I'm not mistaken. But by the way, pull requests are welcome for this. I'm not really an expert in Python or R, so if I've made any mistakes, you're welcome to correct me. Case classes are a really useful feature in Scala that also proved to be very useful. They're often used to represent records in Spark. The idea is, this case keyword says, not only am I just defining a regular class, but I want you to automatically take all these arguments and make them fields. I want you to build, add in toString equals hash code, do it the right way, not the hacky way that most of us end up doing. And I also want you to build there's something called a companion object, basically some static methods that are used to do this pattern matching. So I'll be able to do pattern matching on this person type in just a minute, just because I put the case keyword there. And also there's some other things they throw in that are pretty nice. It's a really useful way of just building these little structural classes that hold state. And they're immutable by default, and I would have to put in a var keyword if I wanted, say, first name to be mutable. But I could do that if I wanted to. It's another example of Scala letting you do stuff that you might want to do, but discouraging you from doing it by default. So here I list a few of the things you get. But here, let's see. Let's do some pattern matching with this, and I'll actually do it in Spark. Although I could have done this in just regular Scala. So I'll take my Spark context. I'll turn this. I made up two people here, me and a completely bogus age, and a friend of mine who actually co-wrote this talk, Andy Petrella. He's actually the guy that created Spark Notebook. So we've got two people. We're going to turn them into a RDD by parallelizing this collection over a big cluster. And then I'm going to, oh yeah, here it is, map over this collection and pattern match on the person instances and then extract the first, last, and age. In this case, I just do something stupid and return a tuple. But when I do that, I get what you would expect, two tuples instead of two persons. So that's really, and that's really why the case keyword is used both in pattern matching and up here, is really because it gives you this duality of construction and deconstruction, which is just fantastic for getting work done quickly. And like I say, case classes are often used in Spark to represent the schema of your records. Okay. We're doing for time. All right. Yeah, and some of the other, really none of the other three languages actually support anything like this at all. They support things like regular expression parsing of strings, which is our old standby, but not this sort of structural decomposition. You'd have to go to something like Haskell or ML or Erlang to do it. Or Clojure now has this facility. So one of the big arguments, of course, in our industry is whether you should be statically typed or not. I don't want to get into that argument here, but what I will say is it does have some convenient properties in this case. First of all, Scala will infer types in a lot of situations, not all. Now, Haskell can actually do it in almost all situations. But here, I didn't say anything about the types, but it just inferred that I was working with integers, kind of a trivial thing. And if we look at one of our examples from before, there's nothing in here at all about types in this grouping by primality example, and yet it infers correctly and conveniently that I have an RDD when I'm finished. And notice that you can actually use the tuple quote things, or rather parentheses things in the type signature as well. So this is actually a tuple 2 is the record type, and RDD is like a collection of tuples. So I actually did some stuff with the Python API not long ago, and it actually was really kind of frustrating that when I would do something like this, which is, the syntax is very similar, I wouldn't quite know what I had when I was done, and I always ended up like printing the first 5 or something just to see what I ended up with, whereas at least here I know what the structure is. Yeah, so here I described that a little bit more detail. You could also write that signature like this if I evaluate this so that you can see a little better. If it's still there. There it is. Yeah, so I could have written that type signature like this, but it also lets me write the same sort of special syntax like I use for values as opposed to types. So for me, this is a nice balance of inferring types to keep that stuff out of my way most of the time, but also catching a lot of errors and telling me what I need to know when I need to know. Yeah, and like I mentioned, it was kind of a hassle not having this in Python. In Java, of course, you can statically type, but you have to be more explicit about typing most things, except for like lambdas and stuff. And R is also a lot like Python, it's dynamically typed. One of the interesting things you run into when you do Java, this is kind of a technical point for Java versus Scala, is Scala actually gives you the illusion that all the primitives are regular object types, reference types. You write like int dot, or parse, or what's a good example? You do it like int dot to float or something if you want to convert an integer to a float. Whereas in Java, it's very clear that you're working with something that's entirely different from the type hierarchy. But there are cases where you have to do these boxing conversions to go from like a primitive int to an integer when you put it in a collection. And that kind of duality doesn't exist in Scala. You can just have a list of strings or a list of ints, and it just works. Now, what it's actually doing, though, it's not completely perfect. It is actually wrapping these integers which is really bad in big data when you've got billions and billions of integers. So it's not a perfect solution, it's a convenience for us. There is an annotation called specialized. Here I'm clicking things again. Let me just point at it right there. That will say, all right, actually I want you to generate customized implementations for A, B, and C, like integer float, integer double and long or typical, that won't do the boxing, but it also is not a perfect solution. But nevertheless, it's nice that I can just uniformly treat primitives and reference types identically. Every method actually always returns something. Even when you would normally return void in Java, you can return unit in Scala, which is a type that basically functions the same way, but it gives you a uniform syntax, which makes your thinking more uniform. And we also get really elegant, surprisingly elegant tools for creating domain-specific languages. This is one of the things that Ruby's famous for, that you can kind of make little languages that are embedded in your Ruby code that look like something that a domain expert would write. Because test tools are a great example of this. If you've ever looked at RSpec in Ruby, or I forget what some of the other tools are called. Better than Python even, but for some reason Scala happens to have a number of facilities that even though it's statically typed, it's actually really nice for writing these little domain-specific languages. And the example I have here is actually one that it's basically an implementation in Scala of a Python API that was basically copied from the R language, and it's called the Dataframe API. It's basically the way to do SQL queries in Spark. So you start by doing some imports that aren't really that important for us to go into, but the one thing that is important is let's call it the entree to this API is something called the SQL context. And once you have that created, I'll go ahead and do that again. Actually, I think I won't do that because I probably haven't evaluated all the cells in front. You can see this output that you're seeing is because I just ran the whole thing a little while ago. I'm going to use the SQL context to read some JSON data. So I need to figure out where it is, and I set up an environment variable in advance to tell me where it's located. This is like the typical Java system environment call. To get an environment variable, you can see it's pointing to this directory here. Nothing too fancy. But the SQL context gives me the ability to get a reader, and then I can say, all right, I want to read JSON. And here is the JSON file that represents airport data for commercial airports in the US. And the nice thing about this is it actually infers a schema from the JSON files. So here's the schema it came up with based on that data. So the airport is like, the names we're used to, like O'Hare, city, country, latitude and longitude. IATA is the codes you see on your tickets, like ORD for O'Hare, ATL for Atlanta, and things like that, and so forth. We can actually ask it for some of the records. So if you do airport show, it starts printing out things that you're used to seeing if you've ever worked with, like, one of these database interactive tools. It just prints out the first 20 records. And caching is something, this is where the abstraction leaks. You have to tell Spark, look, I'm going to work with this data over and over again. Don't keep rereading it every time I do a query. Just cache it in memory. So here's our, the first 20 records for this airport data. And we can actually write typical SQL queries. You can just do SQL and then a string as your regular SQL query. That's a method available on this airport data frames. Or we can use this idiomatic API. And this is really kind of the point I was getting up to. This API is very similar to the way you would write it in Python, which is an entirely different language, where they have this sort of dollar idiom for saying, I want to group by the state and country, and then I want to count the size of those groups, and then I want to order by the count descending. So it's a sort of an idiomatic way of writing SQL, a little bit more type safe than just embedding a string that you won't know until runtime whether you got it right. And when you do this, if you run that query, print the schema, nice little tools for seeing what you ended up with. So state and country were my keys for grouping, and then the count. And then here's the descending count of the results, where it turns out Alaska has the most airports. They're mostly like these little bush airports out in the middle of, like, Denali National Park. I was about to say Kilimanjaro, but a little off there. And Texas is up there, California, and then so forth. Here's Illinois, I guess, actually, 88. Okay. But the thing is, I could have also written this as a SQL query, and it would have been parsed to SQL, and it would have gone into the same runtime. But they've used this. I guess technically you could say this is more of a fluent DSL or fluent API than an actual DSL. You know, there's some debate about those terms. But the point is that when you need to do something that hopefully will be familiar to people coming from another language community, and you want to, or even a domain where they think in terms of some sort of like rules or tax law or something, the language supports being able to build that kind of stuff really nicely. But to be fair, you could have done this in Java too, so it's kind of a lame argument, but it's the best I could come up with. Anyway, so it was actually borrowed. This API was inspired by a Python API called DataFrames, which was actually inspired by an R API with the same name. Okay, let's see, how are we doing for time? I want to make sure we have plenty of time. All right, we're actually nearly done. So I broke this into two halves, and I'm not going to go through the second half because we're almost out of time. The reason I call this a few other things is the stuff that's after this is really valuable for regular like Java versus Scala developers, but actually less useful for big data people or data scientists. Like, for example, where does it go here? Well, gosh, sometimes it's hard to scroll. I'm not sure I can find it quickly, but, well, the things I was going to mention are like recursion. So Scala does loop unrolling tail calls automatically for you. That's not really something you ever use in big data because usually your system is doing any sort of iteration, not you yourself. Things like that are, there it is, tail recursion optimization. Actually very useful if you're a regular developer, not so important if you're a data scientist. And so what this actual section turned into is just a laundry list of all the things where I think Scala is better than Java. So just personal preference, I guess. But I think there's some interesting things to consider here for design rigor, like sealed class hierarchies are really the idea of, what if I declare an abstraction and I only want to be able to declare subclasses and never let anybody else declare something else as a subclass because there can only be the ones that I'm declaring. A good example is something called the option type, which is an alternative to nulls, where I either have something, and that's going to be inside a sum, or SOME, or I have nothing, and that will be inside a none. And there's no middle ground. We're not worried about the law of the excluded middle, if you know what that is. We're going to assume it can only be in those two states. So I'd like to be able to define an abstraction that captures that, but never let anybody else possibly add a third subtype. And Scala has a nice facility for this. They're called sum types, to be technical. Anyway, let me go to the bottom, which is the few things where Scala isn't so great. And just to prove that I'm not a complete Kool-Aid drinker. And some of these, actually, if you're really interested in them, especially if you're doing Spark, I did a talk at Strata San Jose, and here's some links for those slides if you want to see those, where I go into a lot more detail than I can talk about now. Well, one thing very practical is that R and Python have much richer data libraries than Scala and Java do. So there's a lot of stuff you just don't have with Scala and Java, like really good charting libraries. It's hard to argue against that. But the JVM itself has some issues. It turns out that the fact that arrays are indexed by integers is a huge pain in the ass. Because if you think about it, that means you can never have more than 2 billion of anything in an array, because we also don't have unsigned types. And if you have like a byte array, like you're serializing some big object into a byte array, you're stuck with 2 gigabytes, is how big it can be. And yet, Amazon just rolled out 2 terabyte, instances in AWS, right? So we're back to kind of the problem we had with DOS. Boy, I'm really dating myself here. It used to be with DOS, why would anyone need more than 640 kilobytes of memory? Well, we pretty much figured that out quickly, that no, we actually need a lot more. So they came up with all these crazy schemes to layer indirect addressing of memory segments, and that's kind of what we're stuck with. You can't just allocate like a 40 gigabyte array anymore. You have to break it up. So this is actually a real problem that we don't have long indexing. It turns out that the JVM memory model, its garbage collection, the way it lays out objects is really flexible, really powerful at service really well, but it completely sucks for big data. And the problem is, when you have billions of the exact same thing, you don't want to use the regular model. So just as an example, here's a diagram of what a person type might look like in memory. Or I have some reference to a person instance. Maybe the person has a name that's a string. That's another reference off in memory somewhere else. Their age is an integer. I can inline that, or the compiler will. But if I have a pointer to their address, well, that's a reference to yet another object that has its own stuff, like other strings. It turns out every single arrow here is a cache miss. And I'm doing this billions of times to process these peoples. And all of this stuff is little bits of garbage that just torture in the garbage collector. So what we really want is something like this, where we encode objects in like a single array of bytes that hopefully fit in a cache line on the CPU. And this is actually what Spark has done in the Dataframe API, where instead of allocating stuff that looks like this, they allocate a lot fewer little bits of stuff, and it all fits in a cache line like so. And just quickly how this is structured. Some fields could be null, and so they have a bit field for that. So if a field happens to be null, there won't be anything represented in that field in the rest of the record. And then they have 8 bytes per field for what's left. If it's a primitive like a long that fits in 8 bytes, they'll just inline it. Otherwise, the value in that 8-byte field will be an offset into this variable length section for things like strings and stuff. So this is not only far better for cache performance, it reduces the amount of garbage and just makes the thing. They're getting like factors of 100 improvement in performance just by doing these kind of optimizations. And the version of Spark that's coming out this summer, Spark 2, is going to add another 10x or more performance by doing things like those little queries that I showed you. They're just going to generate bytecode for those. They're not even going to compile them to like, method calls and stuff. They're just going to generate bytecode for those kind of queries to get it down to this absolute bare essence. So lots of cool stuff you can do when you have good abstractions and then you layer underneath it, lots of room for optimization. There's also some weird problems with the way the REPL works, the interpreter, that is really causing a lot of pain for one of my big banks in New York. We may have to actually re-engineer the REPL to work better for really big data sets. Anyway, probably out of time here, but so this is basically my argument for why Scala is actually a really good language, not just for engineers, but for even data scientists. But like I say, it's not perfect. So thank you very much.